Hello everyone, I am Revan and I am going to talk about our work entitled Few Short Visual Relationship Colocalization. This is a joint work with Vaibhav, Mayank and Anand. Consider this bag of 4 images. Can you identify the visual subjects and objects connected via a common predicate in each of these images? We as humans could possibly do this very easily. The goal of this work is to address this problem automatically. We refer to this problem as visual relationship colocalization or VRC in short. To be precise, given a bag of B images, each containing a common latent predicate P, our goal is to localize visual subjects and objects connected via P in each of the image of the bag. We solve VRC in 5 steps. In step 1, we formulate it as a labeling problem. To this end, given a bag of images, we construct a fully connected graph by treating each image in the bag as a node. The label set of each node is the set of all possible visual relationships in that image. And the objective is to select the common visual relationship for each image from its label set so that the total cost of selection is minimized. But how do we get the label set for an image? We use faster RCNN to get object proposals for the image. We then create all possible pairs of object proposals and treat them as potential common visual relationships. In this way, all possible visual relationships between the detected objects in an image are in its label set. Once we get the label set, we need to find a way to calculate the cost of label selection. For this, we first encode each object pair in the label set into visual relation space using vTransE, and then train a relation network in an episodic way to compute the similarity between the visual relationships. As an example in this slide, if we select visual relationship L43 from image 4 and L12 from image 1, we will first get the vTransE encoding of visual relationships as F43 and F12. We then use the trained relation network to get similarity score R. The cost of this selection is negative of similarity R because we want selection having similar relationships to have low cost and dissimilar ones to have high cost. We train the relation network in an episodic way, taking one training bag at a time so that it can generalize well to unseen predicates during test time. We use binary log regression loss with gradient descent to train the relation network. During training, the relation network learns to increase the similarity score between visual relationship pairs which share the common predicate of the bag and to decrease the similarity of all other pairs. During inference stage, we use a greedy algorithm. For a bag of images, we first divide the whole bag into small subproblems of smaller bag size. We solve the subproblems and sort the possible labelings according to the cost computed using relation network. We then pick the top k least cost labeling from the subproblems, and then combine them greedily to get the labelings for the larger bag, and finally pick the least cost labeling for the whole bag. This way, we avoid exponential time complexity of inference. We observe that on VRRVG dataset, our best method achieves top colocalization results surpassing other baseline approaches. This can be attributed to two factors. Firstly, using vTransE to get a more semantic representation of visual relationships in the relation space. And secondly, the meta-learning based episodic training, which allows the model to generalize well on unseen test predicates. Here are some visual results using our method: biting, balancing on, following, and sniffing. To summarize, we introduced a novel task of visual relationship colocalization. We proposed a novel meta-learning based optimization framework to address the problem of VRC in few shot setting. We firmly believe that this work will open up several future research avenues. The code of our approach is publicly available and you are welcome to check it out. Thank you.